Welcome to the MSPPy tutorial series. So this is the second video in this series. In this video, I will talk about methodology. How do we solve multi-stage stochastic programs? So let me first distinguish two different problems. One is the true problem and the other is the discretized problem. As I mentioned in the first video, the underlying data process may follow a log normal distribution or autoregressive process, which means that the process sometimes has infinite number of possible realizations. Such problem is not amenable for a finite representation in a computer and should be discretized. So we call the original problem as the true problem and its discretization as a discretized problem. All right, so here is a standardized four-step procedure to solve multi-stage stochastic programs. So we start with building the true problem, and then we discretize the true problem and use whatever solver or whatever algorithm to solve the discretized problem. In the end, we evaluate the obtained policy on the true problem. There are certainly some variations to this procedure for different solving algorithms. We'll go through all the steps in details later on. But what I want to point out here is that whatever solver you use, it should always imply an implementable feasible policy for the true problem. Okay, so and then you can do this step 4, which is crucial because you really need to understand the solution you obtain from solving the discretized problem. What does that solution mean to the true problem? Because your real interest is to solve the true problem, right? You can actually see some papers or software packages, they often start with a discretized problem, like the data process follows a scenario tree, and they just solve the problem with respect to that scenario tree. So the solution they obtain from solving the discretized problem may mean nothing to their original true problem. All right, so this is one uniqueness of the MSPPy package. Now, let's go step by step. So for the first step, building the true problem, it is pretty straightforward. You just model the data process again, a log normal distribution or autoregressive process or other reasonable modeling. And then embed your data process to the MSLP. All right. So if you've used our MSPPy package, you will find typically you spend majority of time in step 1 in programming because for the other 3 steps, we have some built-in functions to do that for you. All right, so step 1 is the most complicated one in implementation. All right, so we will get there. Now let's look at step 2. Which is discretization. So here is an overview of the techniques we've used for discretization. For stage-wise independent process, we will discretize the process by sample average approximation. On the other hand, for Markovian process, we'll see there are 2 ways to embed it to the model. One way is by adding additional state variables and transform the problem into stage-wise independent and then discretize the problem by SAA. Another more general approach is to use Markov chain approximation or MCA. So sample average approximation generates RID samples and uses sample average to approximate the expectation. Theoretically, we have some sample size estimation in order to obtain an absolute optimal solution to the true problem. But in practice, such thing is never applicable, and we should really understand what does the solution mean to the true problem. Okay, so again, that is why the step 4 is crucial. So now, for the Markovian process, oftentimes in practice, the Markovian data process eta t can be modeled using some time series equations. So here are some examples. So if the considered process is linear, like this vector autoregressive model or vector autoregressive model with multiplicative error, plus if it appears on the right-hand side of the constraints, we can then add additional state variables and reformulate the problem into stage-wise independent. All right, because after you reformulate, the uncertainty in the reformulated problem is just a white noise. All right, so in that way, the problem is transformed into stage-wise independent, and we can then discretize it by SAA. In addition, a recent development for this approach is to consider the dual problem. Then the uncertainties in the objective for the primal problem are then transformed into the uncertainties on right-hand sides for the dual problem. So if you have uncertainties in the objective, you cannot just add that eta as additional state variables because it will destroy the linearity. So, but you can still implement this approach on the dual problem instead. All right. So this new approach is currently being developed by Yi Chen, and it'll be available in the near future. All right. So this is the TS approach or time series approach, which has some limitations. Now let's look at a more general approach to discretize the Markovian process. So in this MCA approach, the idea is to find some representing centers in a sample space, or you partition the sample space so as to minimize the so-called quantization error. And those representing points will be our Markov states. After that, the transition matrix can be just calibrated by simulation. So here is a non-convex problem to find those optimal representing centers. So let's first look at the inner minimization problem here. So eta t is the original random process in stage t. Mu tk is a bunch of centers representing the partition in stage t, where k is the center index. And then we take the minimization over k, which gives you the distance of the original process and its closest center in stage t. So essentially, it tells you how much error we have in stage t. And then we take summation over t. So this term gives you the overall error. Okay, and remember, eta t here is a random process, so we take expectation over eta. All right. So in the end, the outer minimization just says to minimize the total error or quantization error. All right, and this is done over all partitions. All right, so this is the Markov chain approximation. So far, MSPPy has two ways to solve this non-convex problem. One approach is to use sample average approximation. So we replace the expectation by this sample average. You can actually find the objective of the SAA problem in each stage is identical to a k-means problem. We can then use the Loyal's algorithm to solve the problem. Another approach is using the stochastic approximation or robust stochastic optimization, depending on you want to use a diminishing step size or a constant step size. So you compute a gradient with respect to the parameter mu and iteratively update that. So that's pretty much it for SAA and MCA. So after discretization, we have two kinds of discretized problems. One is the SAA discretized problem. So essentially, we replace the expectation in the value function by the sample average. All right. The other is the Markov chain discretized problem. So essentially, it replaces the conditional expectation by a weighted average, which is implied by a Markov chain. All right. So that's it for step 2. The next step is to solve the discretized problem. But probably the most well-known algorithm to solve a discretized MSLP is to use SCDP. So what is SCDP? So it is an algorithm that leverages the convexity of value functions and approximate them by piecewise linear functions. All right. So it is an iterative method. For each iteration, we have the forward step to generate trial points based on current approximation of value functions. And in the backward step, we solve all the subproblems at those trial points and update our approximation. And this algorithm is proved to be convergent. Okay? The more important thing of this SDP algorithm is that the cutting planes we obtain from solving the discretized problem implies an implementable feasible policy for the true problem. So how do we achieve that? We achieve that by using definition. So for almost all realization of the process, we can actually associate a decision vector by solving a sequence of subproblems recursively with those value functions approximated by the obtained cutting planes. So by the complete recourse condition, those problems are always feasible. All right. So that's how we get a policy for the true problem. For Markovian problem, it is a bit more involved since the value functions are only approximated at finite number of Markov states, and they are not convex with respect to the Markovian uncertainty eta t. Therefore, a workaround is to use the cutting planes at the closest the Markov state to the realization of the true process. In this way, it still imply a good, feasible, implementable policy for the true problem. All right, so that's SCDP. Another class of algorithms to solve a discretized MSLP is to construct a single deterministic but large linear program. So assume tau is the constructed scenario tree, no matter stage-wise independent or Markovian. We associate a single decision vector x and yn with every node in the tree. We then enumerate all the scenarios and construct the so-called extensive formulation. So this approach does not rely on any advanced technique in optimization, but clearly it suffers from exponential complexity because as we increase the number of stages, the number of scenarios grow exponentially fast. To make things worse, the extensive formulation approach only gives you an implementable feasible policy for the scenario tree rather than the true problem. Okay, so that leads us to the rolling horizon algorithm we developed. Now, instead of considering a static discretization, we let the discretization itself adapt to the true process. Specifically, for any realization of the true process similar to what we did in the SCDP algorithm, we solve recursively a sequence of problems. As we move forward in time, we construct a dynamic scenario tree which is rooted at the current value or current realization of the true process and construct the corresponding extensive formulation. In this way, we always move along with the true process, and therefore we solve the true problem. All right? And in addition, in order to deal with the exponential complexity with solving this extensive formulation, we can actually make this dynamic scenario tree small. For example, as shown in this plot, we only branch the next stage, since the next stage is the immediate future that probably matters the most. All right. For the later stage, we just sample once based on the conditional structure. Then if you solve the problem using this kind of dynamic scenario tree, the resulting algorithm is still polynomial with respect to the number of stages. Okay? We now generalize our methodology to the mixed integer setting. For those two LP solvers, one based on extensive formulation and the other based on rolling horizon algorithms, we can just add integrality constraints and nothing else is different. For SCDP, we have this well-known generalized SCDP in the mixed integer setting, the so-called XDDIP. So here is the mixed integer subproblem we ought to solve for each stage. All right, so here you can see we have this additional integrality mixed integer constraint. So the simplest way to solve this problem is to consider its LP relaxation and just uses the Banner's cuts, but the Banner's cut can be very loose. A much tighter cut is to relax the this linking constraint zt equaling xt minus 1 and consider the Lagrangian dual problem, which is the max min problem. So the outer problem here is unconstrained and is concave with respect to pi. So any pi will provide a feasible cut. In particular, if we just use the Cali V obtained from the dual solutions of the LP relaxation, we get the so-called strengthened Banner's cuts. All right. Lastly, we can also use the level method to iteratively search for the best pi. That'll give you the so-called Lagrangian cuts. Furthermore, if we binarize the state space, then the Lagrangian cuts are guaranteed to be tight. So in those paper, it shows if the binarization is granular enough, under some mild conditions, solving the binarized discretized problem provides an absolute optimal solution to the discretized problem. But again, we need to understand what does the obtained policy really means to the true problem. Since the obtained policy is in a binary space, we should actually we need to revert the policy into the original space. How do we do that? The basic idea is to find the closest binary representation and then use the cutting planes at that binary point. All right? And then you just solve those subproblems recursively, just as we did in the classical SGP. Now, what do we have now? So we have the SCDP, SCDIP, and the rolling horizon algorithm in our methodology to solve the discretized problem. All right? And all of the methods generate a feasible implementable policy for the true problem. Okay? So we can do the policy evaluation, which is step 4. By using simulations, we can get a statistical upper bound. All right? And besides, if the true problem is discretized by SAA, we can randomize SAA to generate a statistical lower bound. On the other hand, for the Markovian case, it is not possible to do that as far as we know. We can also evaluate our policy by comparison using pairwise t-test. All right, so that's it for the methodology. I know I have skipped a lot of details. If you want to dig in more, I encourage you to read our MSPPy paper. The link of the paper is in the video description below. So in the next video, I'm going to introduce the MSPPy package to you. I will explain the syntax and basic features of this MSPPy.